Welcome to the next chapter. It is Organic Chemistry 2. Now in Form 3 we studied Organic Chemistry 1 and we said that organic compounds are compounds of carbon. The element carbon makes a huge part of the universe, both in the living and non-living systems. In organic chemistry we study various families of organic compounds, and the important thing to note is that each family is identified by a functional group. Now it is this functional group that gives members of each family their physical and chemical properties. So you will notice that members of the same family show consistency in their chemical behavior. In Form 3 we looked at a family called hydrocarbons and we defined them as compounds of carbon and hydrogen only. The hydrocarbons are grouped into three. Alkanes have single bonds and we call them saturated hydrocarbons. Alkenes have double bonds and we call them unsaturated. Similarly, alkynes with triple bonds are unsaturated hydrocarbons. Now in Organic Chemistry 2 we shall study two families: alkanols, commonly called alcohols, and alkanoic acids, commonly called carboxylic acids. And we start with alkanols. Now alkanols belong to a class of organic compounds which contain carbon, hydrogen and oxygen. Alkanols contain hydroxyl group, the OH, which is the functional group. Now this functional group determines the chemical properties of the alkanols. Alkanols have the general formula CnH2n plus 1 OH, where N can be 1, 2, 3, 4 and so on. Alkanol is the IUPAC name, while alcohol is a common name. You could look at alkanols as derivatives of water and hydrocarbons, whereby one hydrogen atom in, say, an alkane is replaced by an OH group from water. For example, if I have ethane there, and then I have water molecule on the other hand, suppose the ethane loses one hydrogen, it forms an alkyl that we call ethyl, and water loses one hydrogen atom and it forms a hydroxyl group. Now if these two combine, we'll come up with an ethanol. Again, if I have propane and water, if each one of them lose one hydrogen, we'll have a propyl and hydroxyl group. If we combine them, you realize we form what we call propanol. So you would expect the same for butanol, pentanol, hexanol, heptanol and so on and so on. Just like in the other organic compounds, naming of structures and molecules is very important in alkanols. So we look at nomenclature and we shall demonstrate this with the structure that is on the screen now. Now there are rules that govern the naming of alkanols, just like in all other organic compounds. Now the first thing to do is to identify the longest continuous chain, that with an OH group, and this gives the parent name. So the structure has 5 carbons, so the parent name is pentane. Secondly, number the chain in a manner as to give the carbon bearing the OH group the lowest number possible. Now in the structure, if I number left to right, if I number from left to right, that carbon will be carbon number 4. But if I number from right to left, it shall be carbon number 2. So I choose the second numbering. This number is then put in between the parent name and a suffix "ol" is added. So we shall have pentane 2-ol. Notice the use of hyphens. Now if there were more than one OH groups, then we shall have diol, triol, tetraol and so on. If we had 2 OH groups, let's say on carbon number 2 and carbon number 3, then we shall have pentane 2,3-diol. Pentane 2,3-diol, where the numbers 2 and 3 should be separated by a comma. Rule number 3, locate the positions of the substituent groups and name them alphabetically. So here we have bromo on carbon number 3 and methyl on carbon number 4. So we shall have 3-bromo-4-methylpentan-2-ol. 3-bromo-4-methylpentan-2-ol is the name of that structure. Again, notice that brackets can be used to indicate branches in condensed structural formula. In condensed structural formula, we can use brackets to indicate branches. So this structure can be condensed into this. Now, the knowledge of 4 bonds per carbon atom should guide you to know which carbon does the branch fall. Each carbon must be bonded by 4 other atoms wherever there is a single bond, unless there is a double bond. Now try this exercise before we look at isomerism. Draw the structures of 1,3-dichloropent-2-ol, 1,3-dichloropent-2-ol. Secondly, hex 1,2-diol, hex 1,2-diol. Finally, 2,2,3-trimethyl hex 3-ol, 2,2,3-trimethyl hex 3-ol. And then name the structures on the screen. Name the structures on the screen using that IUPAC system we have just described. So if you have done that, let us look at isomerism. And just like all other organic compounds, alkanols exhibit isomerism. They exhibit positional isomerism, in which the position of attachment of the functional group can vary within the carbon chain. For example, on the structures that we have on the screen, the first one there, the OH group, is on carbon number 1, and that structure is pent-1-ol. Another isomer, you can have the OH group on carbon number 2, and there we shall have pent-2-ol is another isomer. When we have the OH group on carbon number 3, we shall have pent-3-ol. Now, can you tell me why it is not possible to have pent-4-ol? Why is it not possible to have pent-4-ol? Does that structure exist? And as you think about that, let's look at the other form of isomerism, and we have chain isomerism. Now, when the OH group is attached to the first carbon, like in the first structure, we had a structure called pent-1-ol. Now, in this molecule, the hydroxyl group is attached to a carbon atom in which 2 hydrogen atoms are also attached. Now, this results in the formation of a primary alcohol. So the first structure there is that of a primary alcohol, whereby the OH group is attached to a carbon that has 2 other hydrogen atoms attached to it. When the OH group is attached to the second carbon, we had pent-2-ol. Now you realize in this molecule, the hydroxyl group is attached to the carbon atom to which only 1 other hydrogen is attached. Now this leads to formation of a secondary alkanol. So pent-2-ol is a secondary alkanol. When the hydroxyl group is attached to a carbon atom with no hydrogen atom attached to it, we have what we call a tertiary alkanol. And in this structure, the carbon atom also has a methyl group, so that there is no hydrogen atom attached to it. For example, this structure here is a tertiary alkanol, and it is called 3-methylpent-3-ol. 3-methylpent-3-ol is a tertiary alcohol. Next is preparation of alcohols, and we look at ethanol. Now, ethanol can be prepared using 2 ways. The first method is hydrolysis, and we looked at this in Form 3. And ethanol is prepared by bubbling ethane through concentrated sulfuric acid at room temperature. The second method involves fermentation, and ethanol can be prepared by the decomposition of glucose molecules in the presence of enzymes. Now, sugar molecules are broken down into ethanol and carbon 4 oxide by the enzymes in yeast, and this is what happens in the beer brewing industry. This process is referred to as fermentation and can be defined as the decomposition of an organic substance by microorganisms to form alcohol, carbon 4 oxide, and heat. However, a very small amount of alcohol is usually produced by fermentation, actually about 10% by volume. The alcohol content can be increased by fractional distillation of the dilute solution. The 95% ethanol obtained contains 5% of water, which can be removed by using a suitable drying agent such as calcium oxide to obtain absolute alcohol. So let's look at physical properties of ethanol. And ethanol is a colorless liquid which has a pleasant smell. The lower members in this series are liquids at room temperature. For example, methanol, ethanol, propanol, all of them are liquids at room temperature. Alkanols are soluble in water, but their solubility decreases gradually as the molecular mass increases. For example, methanol is more soluble than hexanol. The melting and boiling points of alkanols increase down the group due to the increase in the forces of attraction. Alkanols have a higher melting point and boiling points than their corresponding alkanes with the same molecular formula. This is because the hydrogen bonding between alkanol molecules caused by the functional group OH, hydrogen bonds are stronger than van der Waals forces. We said that in Form 2 when we looked at structure and bonding. And we said that in molecular compounds, the intermolecular forces are either van der Waals forces or hydrogen bonds. Now, whenever van der Waals forces occur, the boiling point and melting point of such compounds is usually lower compared to cases where the intermolecular force is the hydrogen bond, which appears to be stronger than the van der Waals forces. Chemical properties, and we start with combustion. Now, ethanol shall represent the rest of the alkanol, so we shall be looking at ethanol. And ethanol burns in air with almost colorless flame to produce carbon dioxide and water according to this equation. Next is reaction with metals, and ethanol reacts with sodium metal liberating hydrogen gas and a salt. For example, ethanol will react with sodium to form sodium ethoxide and hydrogen gas. Sodium metal reacts with any other alkanol to liberate a salt and hydrogen. The general equation for reaction of metals with alcohols is given there, and generally alkanols react with metals to produce hydrogen gas and a salt. Next, we look at a process called esterification. Now, ethanol reacts with ethanoic acid. Ethanoic acid is a group of organic compounds we call carboxylic acid. We shall look at that later. So, ethanol reacts with ethanoic acid in the presence of a few drops of concentrated sulfuric acid to form a substance with a pleasant smell. Now, the product formed is known as ethyl ethanoate, which belongs to a group of organic compounds we call esters. Now, this process is called esterification. So let's look at that. For instance, I have ethanol and ethanoic acid, and they give me ethyl ethanoate. Ethyl ethanoate is an ester. So let me have the structural representation. Now this is very important. This is the structure of ethanol, by now you know. And this one, the red one, is ethanoic acid. That one you will know. Now they combine in a reversible process in the presence of concentrated sulfuric acid to give this structure. Now I'm using different colors so that you can see where each skeleton goes. Now this is what I'm calling an ester. This is ethyl ethanoate. Now in the formation of esters, the alkyl part, that is the blue part, comes from the alkanol, and the alkanoate, the red part, comes from the alkanoic acid. Although the structure and naming appears to be reversed, but you can write or draw that structure in the reverse process, starting with the blue side. Okay, maybe this is harder to see, so let me try structures with different number of carbons. So let me have propanol, 3 carbons, and ethanoic acid with 2 carbons. Now the equation, propanol plus ethanoic acid, should give me propyl ethanoate. We've seen that alkyl comes from the alkanol, so I have propyl. Then alkanoate comes from the alkanoic acid, so I have ethanoate. The alkanoic acid was ethanoic acid, so it will form the alkanoate part of the ester. So we shall have propyl ethanoate. Now my ester is propyl ethanoate. Let me see the structural representation. So propanol is the blue color. Propanol is the blue structure there. It is the alkanol. And then ethanoic acid is the red structure here. Now when they combine, see what goes on. See where each goes. And again the naming of the structure appears like it's reversed. So I have propyl ethanoate. Propyl ethanoate is the structure there. But notice that you can turn the structure to start with the blue side. Try that and see. So the structure doesn't change. Its name will still remain propyl ethanoate. And this is the beauty about organic compounds, that you can write the structures from any side, from any direction, and doesn't change the name of the structure. Now that is interesting. So now attempt this exercise. Write the chemical equations for the following reactions. Name the product and draw the structures. We have methanol plus butanoic acid, and then pentanoic acid plus propanol. Pentanoic acid plus propanol. Now in drawing those structures and naming the ester, the only thing you need to remember is that the alkyl part of the ester comes from the alkanol. The alkanoid part of the ester, on the other hand, comes from the alkanoic acid. Reaction involving alkanols is oxidation, and we are still using ethanol. Ethanol is oxidized by oxidizing agents such as potassium manganate 7 and potassium dichromate 6 to form ethanoic acid. Now in ethanol, acidified potassium manganate 7 turns to colorless, and this is due to reduction of manganate ions, which are purple, to manganese ions, which are colorless. Similarly, orange acidified potassium dichromate 6 turns to green due to reduction of chromate ions to chromium ions, which are green in color. Now the equation for that can be shown there. Ethanol being reduced by manganate ions to form ethanoic acid and water. Structurally, you can see the introduction of the double bond, and you see the attachment of the oxygen there in the oxidation process. That is very important. Now the oxidizing property of chromate 6 is used in some breathalyzers to indicate the level of alcohol content in the breath of motorists. You know about alcohols. So generally alkanols are oxidized by oxidizing agents to form alkanoic acids, which are commonly called carboxylic acids. Reaction of alkanols is dehydration. Now concentrated sulfuric acid reacts with ethanol at 180 degrees Celsius to form ethene and water. Now the concentrated sulfuric acid acts as a dehydrating agent, and the equation for that is shown. Now at a temperature of 140 degrees Celsius, incomplete dehydration occurs in which an ether is formed. For example, ethanol is dehydrated by concentrated sulfuric acid at 140 degrees Celsius to form an ether. Finally, we look at the uses of alkanols. Now alkanols are used as solvents in the preparation of drugs. They can be used as fuels when blended with gasoline to form gasohols used in methylated spirit stores. They are also used in the manufacture of synthetic fibers like polyvinyl chloride and polythene. It can also be used as an antiseptic when used in specific concentrations, like in skin disinfection. We also use pure ethanol as an alcoholic drink only in low concentration. Now, ethanol may be mixed with a certain percentage of methanol when obtained from an uncontrolled brewing process. Methanol is very toxic and poisonous even in small amounts. It causes blindness and death in large amounts. Methylated spirit is an alcohol containing 95% absolute alcohol and 5% methanol. Methanol and a purple dye called methyl violet are added to make the methylated spirit unsuitable for human consumption. Heavy drinking of alcohols causes damage to body organs such as liver, brain, and the heart. But remember, only ethanol is suitable for human consumption, and again in low concentration. The other group of organic compounds that we look at in this chapter are the alkanoic acids, commonly called carboxylic acids. Alkanoic acids belong to a class of organic compounds which contain carbon, hydrogen, and oxygen. Alkanoic acids contain a carboxylic group which is attached to the alkyl group. Now the structural representation of the carboxylic group is as shown here. Notice the double bond attached to the carbon and the OH group. Now this group is the functional group and determines the chemical properties of alkanoic acids. The functional group also distinguishes the organic acids from inorganic acids. Alkanoic acids have a general formula of CN2N plus 1 COOH, where N can be 0, 1, 2 up to infinity. Alkanoic acid is the IUPAC name, while carboxylic acid is a common name. Alkanoic acids are naturally found in citrus fruits like oranges, lemons, and pepper. Methanoic acid is actually present in nettle stings and insect stings such as bees and wasps. Ethanoic acid is commonly known as vinegar and has an acidic content of about 40%. Butanoic acid is found in beef fat, also called butter. Hexandioic acid is found in palm oil and olive oil. Nomenclature of alkanoic acids. And alkanoic acids are named by replacing the E ending of the corresponding alkane with a suffix oic, and then acid is added at the end. The carbon atom to which the functional group is attached is given carbon number 1, and the simplest member of alkanoic acid series is when N is equal to 0, so we shall have methanoic acid. When N is 1, we shall have ethanoic acid. When we have 3 carbons, there is the structure of propanoic acid. When we have 4 carbons, we have the butanoic acid, and you can go on and on to pentanoic acid, hexanoic acid, heptanoic acid, all the way. How are alkanoic acids prepared in the laboratory? And alkanoic acids may be prepared by the oxidation of corresponding alkanols. We had seen that reaction in the study of alkanols. When acidified potassium manganate 7 is used to oxidize ethanol to ethanoic acid, the solution in the flask will be purple before heating, but after heating, the solution in the flask will turn to colorless. Now in this case, the purple manganate 7 ions are reduced to colorless manganate 2 ions according to this ionic equation. When acidified potassium chromate 6 is used, the solution in the flask before heating is orange, but after heating it turns to green. Now this occurs because the chromate 6 ions are reduced to green chromium 3 ions, again according to this ionic equation. However, in both cases, ethanol is oxidized to ethanoic acid. Now, to ensure complete oxidation occurs, excess oxidizing agent and a condenser are used. The condenser ensures that any vapor escaping is condensed back into the flask for further reaction. The equation for that reaction can be shown here. Physical properties of alkanoic acids. And alkanoic acids are soluble in water. The solubility decreases with increase in molecular mass, which results in an increase in intermolecular forces. For example, methanoic acid is highly soluble than hexanoic acid. The members with a low molecular mass are liquids at room temperature, while those with higher molecular mass are solids. Now, as molecular mass increases, more hydrogen bonds are formed together with the van der Waals forces, thus changing the state of the substance from liquid to solid. Ethanoic acid has a higher boiling point than ethanol and propanol, which has the same number of carbon atoms with the same molecular mass. And this is because of its ability to form hydrogen bonds, which are stronger than those of alkanols. So you can see the hydrogen bonds on that structure. Now, the more the number of hydrogen bonds, the higher the melting point because of the structure. However, ethanoic acid freezes at 17 degrees Celsius, forming an ice-like crystals. Now, a pure form of the acid is called glacial ethanoic acid. Chemical properties. Ethanoic acid has a pH of 4.8 and is a weak acid compared to mineral acid because it partially dissociates in solution to form ethanoate ions and hydrogen ions according to this equation. If you look at that equation, you will see that the equation is reversible, which suggests partial dissociation. Mineral acids dissociate completely to hydrogen ions in solution and therefore have a lower pH. Like hydrochloric acid will dissociate completely into hydrogen and chloride ions. Ethanoic acids react with metals to form hydrogen gas and a salt. That salt is an organic salt. For example, ethanoic acid plus magnesium will form a salt called magnesium ethanoate. Magnesium ethanoate is an organic salt and hydrogen gas is liberated. Alkanoic acids react with metals to form organic salt, metal alkanoate and hydrogen gas. Ethanoic acid neutralizes sodium hydroxide to form salt and water. So the reaction is shown here. Ethanoic acid plus sodium hydroxide to give sodium ethanoate, that is the salt, plus water. Therefore, generally alkanoic acids react with alkalis to form salt and water, that is shown here. Ethanoic acid also reacts with sodium carbonate to produce carbon 4 oxide and water according to that equation. The salt formed again is sodium ethanoate. When ethanoic acid reacts with ethanol in the presence of a few drops of concentrated sulfuric acid, what was seen? We formed a pleasantly smelling compound called an ester. Ethanol plus ethanoic acid formed ethyl ethanoate. What are the uses of alkanoic acids? Alkanoic acids are used as solvents just like in alkanols. They are used in the manufacture of drugs and chemicals, as vinegar in flavoring and preservation of food, and also in the manufacture of synthetic fibers such as terylene and dacron. Now we look at another part of this topic that we want to study, and that is the detergents. Now, detergents are substances which improve the cleaning properties of water. They are of two types, soapy and soapless detergents. Soapy detergents are commonly referred to as soaps. They are prepared from either fats or oils. Generally, soap is a salt of carboxylic or alkanoic acid with a general formula shown here. Now, how can one prepare soap in a laboratory? Soaps are prepared in the laboratory by reaction of an alkali with fat or oil, and they are boiled together. For example, when an alkali is boiled with a fat or an oil, a hydrolysis reaction takes place. For example, fat plus sodium hydroxide gives soap plus glycerol. Now, when a fatty acid is hydrolyzed in the presence of an alkali, the process is referred to as saponification. In the hydrolysis of fatty acid, sodium hydroxide neutralizes the acid formed, that is stearic acid, to form the sodium salt of the acid. And this can be shown by this equation. Look at those structures of the fatty acid, and they react with sodium hydroxide to form the soap. The soap is sodium octadecanoate. Remember, we could also have potassium octadecanoate. And then the glycerol there is an alcohol, and it's called propan 1,2,3-triol. Propan 1,2,3-triol. The soap formed, that is sodium octadecanoate, is commonly known as sodium stearate. On the other hand, propan 1,2,3-triol is found in castor seeds oil. But any other oil can be used to prepare soap. Sodium chloride crystals are usually added in the mixture to reduce the solubility of soap in glycerol. And this is known as salting out. We define salting out as the removal of soap from a solution by precipitation. Sodium chloride helps in the precipitation of soap and thus separates soap from glycerol. The soap obtained is rinsed in distilled water to remove impurities such as glycerol, other salts, and unused alkali solution. When a piece of cloth is cleaned in a solution of the samples prepared, dirt is easily removed, unlike when you use distilled water only. So let us look at the mode of action of soaps in cleaning. How do soaps act to remove dirt from clothes? The mode of action of soap in cleaning. Now, the cleaning property of soap depends on its structure. For example, sodium stearate that we've just prepared consists of an oil-soluble long hydrocarbon and a polar end which is water-soluble. This is shown here. Now, a soap molecule has two parts. The first one is a hydrophobic end, and a hydrophobic end is a hydrocarbon chain end which is non-polar and has no attraction for water, or we can say in simple language it's water hating. The other part is hydrophilic, and hydrophilic end is a carboxylate end which is polar and is attracted to water, or we can say it's water loving. Now this end is in fact negatively charged in water. So this is a general structure of a soap molecule. When in water, the soap dissociates into sodium ion and carboxylate ion. The non-polar end is oil soluble while the polar end is water soluble. If you take this to be the structure of a soap molecule, we would say that it has a long non-ionic hydrocarbon chain and a short ionic end. The hydrocarbon end is non-polar and hydrophobic or water repelling. The ionic end is polar hydrophilic or water attracting. When soap is added to water, the molecules arrange themselves with the non-polar hydrocarbon chain away from the water. So how does soap remove dirt from fabrics? Now, to understand this, let us see exactly what happens when detergent is added to water. Upon agitation, the soap dissolves, and this is what is happening at the molecular level. When the garment is put in water, the soap molecules arrange themselves in radial clusters called micelles. The hydrocarbon chain is directed towards the center. Why? Because the dirt molecule is organic and is attracted to the non-polar hydrocarbon chain. On shaking, the dirt molecule is dislodged from the garment and is trapped at the center of the micelle. Upon rinsing, the dirt is removed away and the garment is clean. Now let us look at the effect of hard water on soap solution. Now usually distilled water requires very little soap solution to produce lather, but solutions containing dissolved salts require varying amounts of soap in order to produce lather. Water containing calcium and magnesium ions does not lather readily with soap, and these ions react with soap to form an insoluble product we call scum. Scum formed is either calcium stearate or magnesium stearate. For example, as shown on this equation, the magnesium stearate is the scum. Same case with calcium stearate. The presence of calcium ions and magnesium ions in solution causes permanent hardness of water. When these ions are removed, the water is said to be soft and it will lather easily with soap. Calcium and magnesium ions can be removed from solution by the addition of sodium carbonate, and the ionic equation for the reaction that is bound to take place are shown here. The carbonate ions are from sodium carbonate. Now, we had previously seen the disadvantages of hard water, and we shall not go back to that again. So that next we look at soapless detergents. Now, soapless detergents act as cleansing agent in the same way as soapy detergents by emulsifying the dirt held on an oil or a greasy particles. These are detergents in which the carboxylic group of the soap is replaced by an alkyl sulfonate group. So, for example, you have these structures here where R represents the long chain hydrocarbon. Soapless detergents act like soap in the cleansing process, but they are not affected by hard water and like ordinary soap. Unlike soap, soapless detergents lather readily with water since the corresponding calcium and magnesium salts are soluble. Soapless detergents are manufactured from petroleum products. They can also be made from vegetable oils or fats, which are expensive. During this process, long-chain hydrocarbons are combined with benzene molecules at very high temperatures to produce alkyl benzene, which is the organic part of the soap. Soapless detergents are manufactured in liquids or in solid form, and in order to improve the cleansing properties of soapy and soapless detergents, tetraoxophosphates materials are added. The compounds prevent formation of compounds with calcium and magnesium ions and also fatty acids. Therefore, soapless detergents are preferred to ordinary soap because they form soluble salts with calcium and magnesium ions, and hence they are not affected by hard water because they do not form any scum. Now, but there is a disadvantage, that is pollution of detergents. Pollution effects of detergents. The tetraoxophosphate and other compounds added to remove calcium and magnesium ions during cleaning, when released to water bodies, provide nutrients for aquatic plants like algae and water hyacinth. The population of the aquatic plants grow quickly, making use of the dissolved oxygen in water. Lack of oxygen in the air causes death of aquatic life due to high biological and chemical oxygen demand. Now, in order to control pollution by detergents, some countries have made laws and regulations to ensure safe standards are used. For example, in some countries, non-biodegradable detergents are banned. The next part we look at are the polymers. Now, in Book 3 under Organic Chemistry 1, we discussed that ethene molecules have the ability to undergo self-addition reactions to form a long-chain molecule that we call polyethene. Now, the long-chain molecule is called a polymer, while the unit molecule of ethene is referred to as a monomer. Monom means one, poly means many. Monomers can be of the same molecules or different, doesn't matter. And the process through which the monomers combine to form a long-chain molecule is known as polymerization. Polymers may be man-made or synthetic, or they may be naturally occurring. Rubber, cellulose, wool, silk, and starch are examples of naturally occurring polymers. Now, the synthetic polymers may be made by two methods, and these are addition polymerization and condensation polymerization. In addition polymerization, this occurs when saturated molecules, that is monomers, join to form a long-chain molecule called a polymer without the formation of any other product. One of the monomer, open-end electrons not bonded, form bonds with the neighboring molecules. The case of ethene polymerizing to polyethene has already been discussed under alkenes. One of the molecules of ethene adds itself across the double bond. Other examples of addition polymers are the polyethylene plastics like polyvinyl chloride, polystyrene, Papex, Perspex, and synthetic rubber. Examples of polymerization reactions are shown structurally here. You can see ethene and another ethene. These are two monomers combined to form polyethene. That is a polymer. Note that the polymer formed by addition of identical molecules will have a relative molecular mass that is an integral multiple of that of the monomer. The other type of polymerization is condensation polymerization. In condensation polymerization, identical or different monomers combine to form a long chain molecule with the loss of a small molecule like, say, ammonia or water. Now, the monomer should have at least two identical functional groups so that molecules can join at both ends, thus permitting formation of a chain. An example of a naturally occurring polymer formed in this way is starch from glucose monomers. And this is shown here. A water molecule is usually lost. Next is rubber, and naturally occurring rubber can be obtained from rubber trees. Rubber trees give out a liquid that is called latex, which is collected from cuts in the trunk of the rubber tree. This latex is then allowed to coagulate, resulting in hydrocarbon polymer, which is made up of isoprene. Isoprene is 2-methyl-butyl-1,2-diene, is an alkene. However, synthetic rubber can also be obtained by polymerization of isoprene or use of butan-1,3-diene, phenylethane, in the presence of water. The product is usually soft and hence must be hardened. Formation of natural rubber, and this is an addition polymerization of isoprene molecules. The isoprene molecules are the monomers, and the structure of the monomer, that is isoprene, is shown here. The wear quality of rubber can be improved by a process we call vulcanization, and this involves heating rubber with sulfur. The sulfur atoms form links between chains or rubber molecules, reducing the number of double bonds in the polymer. And this makes the material tougher, less flexible, and less soft. Soft rubber has about 2% sulfur, while toughened rubber contains about 10%. Synthetic polymers have many advantages over natural materials. First of all, they are less affected by acids, alkalis, and water, and also air. They are lighter and stronger. They can be molded into desired shapes easily, and they are also less expensive. However, they have some disadvantages. For example, plastics burn more readily than natural materials. They do not decompose easily, that is, they are non-biodegradable, and this has resulted in environmental pollution, especially by plastics. Some synthetic polymers give off poisonous gases when they burn. For example, polythene gives off hydrogen cyanide and carbon dioxide. Well, so much for that. Let's look at the summary of what we've learned in this chapter. In this chapter, we were largely dealing with alkanols, commonly called alcohols, and alkanoic acids, commonly called carboxylic acid. Alcohols are identified by their functional group OH, while carboxylic acids are identified by the carboxylate group. Detergents are substances that improve the cleansing effect of water, and they have both polar and nonpolar portion of their molecules. They can be soapy or soapless. Soapy detergents are made by means of saponification of natural fats or oils. Soaps are carboxylate salts. Soapless detergents are made by reaction of fuming sulfuric acid with certain alcohols or alkyl benzenes. These detergents are sulfates and sulfonates respectively. We then looked at polymers and said polymers are large molecules formed by union of many monomers. There are two types of polymerization, that is addition and condensation. We then looked at rubber, which is a natural polymer. It has been put to many uses once modified or when used in its natural state. Vulcanization of rubber involves heating of rubber with high-grade sulfur to make the product less flexible and tougher.
Time progressed into the mid-1800s. Telegraphy has been discovered. Samuel Morse has devised the Morse code. They started with telephony, the telephone, sending voice across wires. By the 1890s, things really started to hot up. In those times, guys like William Crookes, various other experimenters, all started playing with this new phenomenon of high voltage using a device called a Ruhmkorff coil and passing this high voltage through tubes that the air had been exhausted from. So in other words, they had removed the air from these tubes and they tried to see what would happen if very high voltages were passed through the slot. Now, There is our cathode ray. You can see the ray appearing across the tube. This is the sort of thing that fascinated the scientists of those days. Now, this is very interesting because this led to all sorts of things. And of course, if you continue to experiment as they were doing, what would happen? Discoveries are bound to be made. And this, of course, led not only to the discovery of the electron, but also the discovery of something that I'm sure a lot of us have had dealings with in one way or another, the discovery of X-rays.